So we're going to continue on with the atom and quantum mechanics. Some of these values we already went over, so therefore it is a review. The principal quantum number is n. It is the row number. The row number that you would see on your periodic table. If you're looking at your periodic table, hint, hint, wink, wink, nudge, nudge, cough, cough, please look at your periodic table. The principal quantum number is the row number. The angular momentum number, also shown with, is as L, and a lot of times I will use a cursive. The L integers are your row number minus 1. Those values of L, or your angular momentum number, correspond to a type of orbital. That is the S, P, D, and F. We showed you some of those ideas and where you can find some of that on your periodic table. Then the magnetic quantum number, kind of the how does it orientate in space? That is your magnetic quantum number, that we have it as M sub L to indicate that. It is the negative of your L value to the positive of your L value using integers. Okay. Orbitals with the same n, principal quantum number, form a shell. Different orbital types are within a shell are called subshells. Now, we didn't really practice this, but if we had a n value of 2, the L values would be 1 minus that, meaning it could be as great as 1. But it is also going to have the 0. The M sub L values, you need to take it for each of the L values. Well, you can't subtract 1. Well, you can, but it doesn't work out so well. Your M sub L value, when it is 0, is also 0. It only has one orientation in space. Okay. If you have an L value, angular momentum number, of 1, you have negative 1, 0, and a positive 1. That means those orbitals have, or the subshells have 3 orientations in space. Okay. They have 3 orientations in space. Also remember that these are values that we are simplifying from the equations that you would need to have that high-end math form. Okay? We're trying to simplify it. Don't try to understand it. We're trying to simplify it a lot for you. Okay? This is what they can look like. I wouldn't suggest not copying down this whole chart because it's a lot. Instead, maybe find the page 221 or table, I think it might be still 6.2 for this version of the book. is that. And as you can see, when your n value is 1, your L value is 0. Your n sub L, or your magnetic quantum number, is also 0. As you go up, your values also increase. You can see these on the periodic table. On the periodic table, row 1 only has what? It only has 2 in it. It only has the S block. The S is associated with the 0, the magnetic quantum number of 0. Okay? Or the angular momentum number of 0. In row 2, where the principal quantum number is 2, you have possible values of 0 and 1. The 0 is your S block, which are groups 1 and 2, which if you look right above lithium and beryllium, it says S block. Okay. If you skip over to boron through neon, it says P block on our periodic tables that we use. Now, that is because the L values are P shape. Okay, we'll talk about the shapes later. The magnetic quantum number, the M sub L, has 3 orientations in space. How wide is the P block? Count boron to neon. How many elements wide is it? It'd be 6. How do you think that divvies out in a nice, easy way? Maybe is it like 2 electrons per orientation? Oh, that would make things really nice, wouldn't it? Because then you would be like 6 across. If I divide that by 2, that would give me 3 orientations. And now then, when you look at your D block, without even looking at this, you're going to find that it's 10 elements wide. So how many different integers for your magnetic quantum number should you have then? 10 divided by 2 is 5. You should have 5 numbers. They are -2, -1, 0, 1, 2. That's 5 integers right there. That's 5 orientations in space. Then when you go all the way down to the lanthanoid and actinoid series, where it's the F block, the weird ones, they're 14 elements wide. 7 orientations in space. Okay? And that's what we kind of work with. That's where it becomes. Not all of the elements will have an F or a D orientations because they're not there yet. They don't have that many protons and therefore that many electrons. They don't have it because they don't need it. So, these are all about patterns. Can you determine the pattern? A without referring to the previous table, predict the number of subshells in the fourth shell, meaning for an element in the fourth row. Label each of these subshells and how many orbitals in each of these subshells. Looking at your periodic table, all of this is there for you. Okay? It's all about patterns. I'm not trying to hide anything. It's all the patterns are there. Okay? So when n equals 4, my next thing would be my L. L is n minus 1. Well, what's 4 minus 1? 3. Meaning we go all the way out to 3. But how do we count to 3? Most people count 1, 2, right? And why don't we count 0? Because there's nothing there, right, with 0. But technically it's there. We just don't usually count it. You know you have the correct number of L values because of how many L values do I have? I have 4. They should match. You know you're on the right path when those two match up. All right. Now the bigger one, and that's the m sub L, the magnetic quantum number. Always start with the 0. It's the easiest. Why? Because it's a 0. Now the 1, we need to find the negative of that, which would be negative 1. And then we increase to integers till we get to that same value. Well, negative 1, then we get to 0, and then just 1. I like to plus 1, okay? Well, it's the same pattern for 2. We start with negative 2, negative 1, integers, none of these halvesies or anything like that, 0, plus 1, plus 2. We're almost done. And now we have to do the same thing for 3. Its magnetic quantum number, the m sub L value, for 3 is going to start with negative 3. After negative 3 comes negative 2. After negative 2, it comes negative 1. After negative 1, it's 0. Then plus 1. Then positive 2. And then plus 3. Now, do we know where the electron resides in? No, we do not. It's somewhere inside one of those orientations, or there are electrons somewhere inside those orientations. As you can see, there's a lot of places for it to hide, right? When we kind of put these things together, which we're not going to worry about putting too much of them, in all reality, you have every quantum number and value from 0 or from 1 to 4. So you could have quantum numbers or that would look like this. Okay, and then what we start doing is we start putting the electrons inside there as a fourth coordinate. If you wanted to give me latitude and longitude, it'd be these really long, weird, abstract numbers. Because you always see that on movies, right? They're like, what do these numbers mean? Oh, they're coordinates. Eventually somebody figures it out that it's latitude and longitude. That's what these numbers are doing. It's taking all that crazy math and kind of funneling it down to a coordinate system to say you should have electrons that have these values of energy. They may or may not have them, though. Okay? Let's look at another example. What is a designation for the subshell that has an N value of 5 and an L value of 1? Okay. Now we're getting a little more specific. Here, we say the N is 5. We're also indicating our L value is 1. Does it have the other ones? Yes. Yes, it would. But this question isn't asking us to write out all of them, is it? If it wanted it, it wouldn't have given us the L value. Okay? Indicate the values of m sub L for each of these orbitals. How many orbitals are in the subshell? That'd be 2, 0, and 1. Indicate the values. -1, 0, and +1. Okay. These are the orientations in space for when n equals 5, L equals 1. We could also write it as this kind of crazy thing. Something like that. How many different numbers can I have written? I have 3 variations for that. 3 orbitals in the subshell. This is not always necessary to write out. This tells us the majority of what we need to know.